In this tutorial series, I'll show you how to use deep reinforcement learning to train this robot vacuum to up this room. I'm going to focus more on the reinforcement learning aspects and less on Unity. As a prerequisite, you need to know some basic Unity. There are plenty of Unity tutorials on YouTube. Now for this room, you can easily make this room with 4 walls, a floor, and the robot is just a cylinder with a red cube. But if you want to get this asset, let me show you how. You can get the living room asset from learn.unity.com, click on Pathways, scroll down and click on Unity Essentials. From here, if you're not familiar with Unity, this is a great starting point. But if you just want the asset, let's go to this one right here, Open Unity Essentials project. And then if we scroll down on section number 3, this talks about how you can get the same living room asset that I'm using. The second thing that you need is Unity ML Agents. This is Unity's own reinforcement learning library. So go ahead and search for Unity ML Agents. And instead of going to their GitHub page, go to the official docs and then make sure the version that you have is the latest one. Scroll down and go to Get Started and then click on Install ML Agents. Go ahead and follow these instructions and get ML Agents installed. Once you get this installed, you're ready to go. Let's take a quick look at our environment. We have a bunch of stars laid out throughout the room to represent the spaces that the robot vacuum needs to clean up. So essentially the robot's objective is to collect all the stars as efficiently as possible. The green lines around the robot represents its sensors. There are 16 of them. 16 is an arbitrary number that I selected. We can definitely increase or decrease that granularity, but I found that 16 is enough for the robot to sense the stars around it. Now let's talk about the robot's movement. It can either turn to the left, turn to right, or move forward, or a combination of them. Now let's look at the stats at the bottom here. Episodes represent how many times the robot has attempted to clear this room. The step count is how many actions that the robot has taken. Not moving also counts as a step. We do have a limit on the max number of steps per episode. I think I set it to 5,000, but that number could be adjusted. The reason why we have a max limit is because during training, it's possible for the robot to not find some of the remaining stars and basically get stuck forever, maybe going in circles. So once it hits the max number of steps, we end this episode, bring all the stars back, and resume training. We have a timer here, and also we're tracking the best time. We're also tracking the rewards or penalties, and we'll talk more about this reward system later. Dirt is just the number of stars remaining on the floor. So we talked about what the robot can see, what its objective is. The only thing left is the robot's brain. Now let's talk about that. When we talk about the vacuum robot's brain, we're essentially talking about training a deep neural network. I'm going to give you a high-level overview of how this works. If you want deep explanations of how these reinforcement algorithms work, I'm going to pop up 2 separate videos that you can choose from, and those contain very technical details. But here, let's do a high-level explanation. So the input of the neural network is what the robot sees, and that is called observation. The robot has 16 sensors. We essentially have 16 separate nodes representing the sensors. Each node represents a single sensor and it's a normalized number. For example, let's say this sensor right here. Let's say this is 7 feet away from the robot and the robot's maximum sensor distance is 10 feet. So you'll have 7 divided by the max sensing distance of 10 and it'll be a 0.7. So one of these nodes will be a 0.7. Why are we using normalized numbers? First reason, neural networks don't like big ranges of numbers. Let's say we drop the robot into a gigantic room. Instead of 7 feet, it's 7,000 feet away. So you have a big range of something that's 1 feet away and 7,000 feet away. and neural networks don't like this huge range. The other reason is if we use a normalized number, even if we drop the robot into a bigger or smaller room, all we have to do is increase the sensor's max sensing distance, increase or decrease its max sensing distance, and we can reuse the model to make decisions. So even in a bigger room, the start is still at a relative distance to the robot. Since this is a deep neural network, you're going to have hidden layers, and the number of hidden layers and the number of nodes within each layer, those can be adjusted based on the complexity of the environment. Now the output of the network are going to be the actions. So you have observation, what the robot sees, and then based on what the robot sees, what actions the robot should take. We have talked about the robot being able to move forward. So we use one node to represent the forward action. Or we don't have to move forward, so no action. There's also another set of choices. The robot can turn to the left, or it can turn to the right, or it can choose also no action. So these are two branches of actions, two independent branches. Branch 0 and this is branch 1. The robot can select two actions, one action from branch 0, one action from branch 1. Now what are the actual values that gets outputted? It's actually a probability distribution. So let's say at this current observation, there's a 30% chance of choosing the forward action and 70% chance of not taking action. Since this is a probability distribution, this of course needs to add up to 1. Same thing occurs here. Let's say this one has a 40% chance of going to the left and 0.1 chance of moving to the right and a 0.5 chance of not doing anything. Again, this needs to add up to 1. When we first initialize the neural network or the weights and biases in the network, the outputs are pretty much random. At the beginning of training, this randomness helps the robot explore. As training progresses, these percentages are adjusted based on rewards. We have what the robot sees. Based on what the robot sees, it takes certain actions. Let's say the action that it took was a forward action and it produced a positive reward. So it would make sense to adjust this percentage up by a little bit. Let's say it goes to 0.4. And since this is a probability distribution, as you adjust one number, the other one naturally goes down. And similarly, because we are taking two actions at the same time, let's say we were going forward and turning left at the same time, and that produced a positive reward. We also bump this up by a little bit. And these two numbers will evenly go down by 0.1 or half of that. Again, this is a very high-level explanation of how reinforcement learning works. If you're interested, I encourage you to take a look at my other videos that does a deep dive into the PPO algorithm or DeepQ learning algorithm. Okay, in the next video, I'm going to show you how to translate all this into Unity and into code. Hope to see you there.